Dear students, this is the third session of the chapter Stereochemistry, and in this session you will be learning about assigning configurations, plus or minus notation, small d or small l notations, or capital D or capital N notation, R and S notation using sequence rules, and also racemization. You all know that we are talking about spatial molecule, the three-dimensional arrangement of the molecule. So it is very difficult to assign the exact configuration of a molecule. So we will see what do we mean by the term configuration. The actual arrangement of atoms or group around the asymmetric center in space is configuration or absolute configuration. So absolute configuration is the actual arrangement of atom or group around the asymmetric center in space. So it is very difficult to find out the absolute configuration of a molecule. We are talking about optically active molecule. It is impossible to assign absolute configuration to an optically active compound. So it is done by relating the compound with some reference compound whose configuration is arbitrarily assigned. So this is called relative configuration in comparison with the reference, that is called relative configuration. Now plus and minus or small d and small l are used to represent the sign of the optical rotation. So in the last session we have seen already that an optical isomer can rotate the plane polarized light either towards the right or towards the left. So to which direction it is rotating? If it is rotating towards the right side, we represent it by plus sign or we write D form, or D stands for dextro form. Or if the optical isomer is rotating the plane polarized light towards the left side, we give minus sign or it is the levo form. The sign of the optical rotation is not related to its configuration. So this plus or minus sign or D or L is nowhere related to the configuration of a molecule. Now, for assigning the configuration of a molecule, we follow two main systems. One is DL notation and the other one is R and S notation. Coming to DL notation, D and L notations are used specifically in sugars and amino acids. Glyceraldehyde is chosen as the standard. We have already seen that the exact configuration is very difficult to find out. So we follow the relative configuration. So the relative configuration will be based on or in comparison with a standard compound. So in DL notation, we follow the standard as glyceraldehyde molecule. If the hydroxyl group is on the right side on the asymmetric carbon atom, then it is called as the D isomer. Here you can see this is the glyceraldehyde molecule where we have 4 group around the asymmetric carbon, is around the chiral carbon. We have one aldehyde group, we have one CH2OH group, we have one hydroxyl group, and also we have one hydrogen atom. So just see the central carbon atom, which is the chiral carbon atom, and on both sides of the chiral carbon atom we have one H hydrogen atom and at the other side we have OH. So if the position of the hydroxyl group is on the right side of the viewer, then we call it as D-glyceraldehyde. Or in the other way, if the OH group, if the hydroxyl group is on the left side of the viewer, we call it as L-glyceraldehyde. So for carbohydrate, for the lowest asymmetric carbon atom is considered and configurations are assigned. Carbohydrate, what is happening? Carbohydrate will be many carbon atoms. So for example, glucose is a hexose where we have CHO, CHOH 4 times and finally we have CH2OH. So there are many chiral carbon atom in that. So in such cases, we follow the lowest carbon atom, the lowest asymmetric carbon atom that is considered, and the position of hydroxyl group on the lowest carbon atom, if that is on the right side, we call it as the D-hexose, D-glucose. Or if it is on the left carbon atom, left side of the carbon atom, we call it as L-glucose or L-hexose. But there is some limitation for this method. It can be used only for simple compounds, not for any compound which contain more than one asymmetric center. Though we say that in sugar we used to follow this method, it is not taken as a standard method for the finding out the configuration of the molecule. Now coming to the next category or next pattern of nomenclature, R and S notation. To determine the configuration, we follow this system also. This is given by three scientists which called Kahn, Ingold and Prolog. So the system itself is named as Kahn, Ingold, Prolog sequence rule based notation, that is R and S notation. So Kahn, Ingold and Prolog introduced this systematic notation. To assign the configuration, an order of priority should be assigned to the atoms or the groups directly attached to a stereogenic center by a rule called sequence rule. We know that around the asymmetric carbon atom there will be 4 groups. Each group will be given priority 1, 2, 3, 4, etc. So based on the many rules, based on the atomic weight, based on the molecular weight, based on the number of double bond or triple bond, many conditions we follow to assign the priority. So we first give the priority for all the 4 group. Then the molecule is then visualized in such a way that the lowest priority group is directed away from the observer and then the remaining groups are observed. Which will be the lowest priority group? The priority group with 4, number 4. So we will be viewing from the side of the 4th priority group. Then if in proceeding from the higher priority group to the lower priority is clockwise, the configuration is R. So we are viewing the molecule from the 4th priority group. Then what are left out? 1, 2, 3 are left out. So then we will be viewing the molecule. What is the order of arrangement of 1, 2 and 3rd priority groups? If the order is coming as a clockwise direction, we call it as the configuration is R. Or if the order is anti-clockwise direction, that will be S configuration. Just like here. So around carbon atom, there will be 4 priority group. 1 we can give as priority number 1, 2, 3 as well as 4. So from the side of the 4th priority group we'll be viewing and we are seeing what is the arrangement from 1 to 3. Now this is like this and this direction is clockwise. So we call it as R stands for rectus. R stands for rectus. Now in the other way, if we are viewing this molecule again from the 4th side, here what we can see? It is 1, 2, 3. It is in the anti-clockwise direction. So this is the S form or S stands for sinister form. R stands for rectus and S stands for sinister. This is how we give the configuration based on Kahn, Ingold, Prolog sequence rule. Now, followed by the rule, if the 4 groups attached to the central carbon, chiral carbon are all different, then priority is given according to the atomic number. An atom of higher atomic number gets the highest priority. Atomic number of atom directly attached to a chiral carbon atom is considered. Like if it is attached, if I, B, R, Cl and F are the 4 group, then I should be getting the first priority. Then Br, then Cl, then F, then oxygen, then nitrogen, then carbon and finally hydrogen. Always hydrogen will be the final group which will be having the 4th priority. If the substituents are groups, the atomic number of atoms directly attached to the C star, the chiral carbon, are taken into consideration. If the first atom of the group attached to the chiral carbon are same, then the second atom is considered. CH2, CH2, CH3 if it is one group, then CH2, CH3 is the second group, then CH3, the methyl group will be getting the lowest priority because in methyl group, the carbon is connected to 3 hydrogen atom, whereas in ethyl group, the carbon is connected to 2 hydrogen and 1 carbon. So we take that group as the highest priority. So if there is propyl, ethyl and methyl group, propyl group will be getting the highest priority, then comes ethyl group and finally comes methyl group. A doubly or triply bonded atom is considered to be equivalent to 2 or 3 such atoms. For example, if you have a carbonyl group, for example, CHO, then the C double bond is considered to be a bond where the carbon is bonded to 2 oxygen atom. So double bond O means C, single bond O, single bond O. Similarly, C double bond C means C, single bond C, single bond C. It is considered as 2 sigma bond connected to carbon atoms itself. Similarly, in the case of triple bond C, triple bond C, it is considered as C, single bond C, single bond C, single bond C. 3 group, 3 bonds bonded to carbon atom itself. We'll have an example here. Look at this molecule. This is butane 2-all. Butane 2-all, butanol, 2-butanol. Around the chiral carbon, we have 4 groups. What are they? One is hydrogen, other one is hydroxyl group, then it is methyl group, then it is CH2, CH3. It is ethyl group. CH2, CH3 is ethyl group. Now, when we give priority for these all the 4 groups, which group will be getting highest priority? We'll see here. Here, the carbon is connected to oxygen. Here, it's connected to carbon. Here, it is connected to carbon and then to carbon. Here, it is hydrogen. So, when we compare oxygen and carbon, the highest atomic weight is for oxygen. So, OH will be getting the priority number 1. Then going to the other 2 group, because hydrogen, as I told you, it will be getting the lowest priority, which is priority number 4. Then in between CH2, CH3 and CH3, which will be getting the second priority. So here what's happening? CH2 is connected to another carbon. Here the carbon is connected to all the 3 hydrogen atom. So this group is bulky and we can say this is getting the second priority. Then of course it will be getting, methyl group will be getting 3rd priority and hydrogen will be getting 4th priority. Now the 4th group, always the 4th priority group should be on the vertical line. That is the line of the viewer. So even if the hydrogen or the lowest priority group is on the horizontal line, we have to bring it to the vertical line and assign the configuration. So in this case, we don't have to bring, it is already there in the vertical line. So directly we can assign the configuration. How we can assign the configuration? We should see how it goes from 1, 2, 3. If we come like this, it will be 1, 3, 2. That is wrong. We should go like 1, 2, 3. So when we go 1, 2, 3, it is clockwise. So we can say this is R butane 2-all, R butanol. So the configuration is R. Now coming to the second molecule, 2-bromobutane. Here again, there are 4 groups. One is hydrogen, one is bromine, then CH3, then CH2, CH3. So we can assign the priority. Bromine will be getting the highest priority number 1. Then ethyl group will be getting second priority. Then methyl group and then 4th priority will be hydrogen. But the hydrogen is there on the horizontal line. So we have to bring it to the vertical line. So how to bring to the vertical line? These 2 groups we can exchange. When we exchange these 2 groups, ethyl group will come here and hydrogen will go here. But we should not do only one alteration. We have to do 2 alterations. When we exchange these 2 groups, these 2 groups also should be exchanged. Otherwise, the configuration of the molecule will change. So here again, this also we should interchange. So CH3 will reach here and Br will go here. Now our 4th priority group is on the vertical line. Now we can see the rotation 1, 2, 3. Now this is 1, 2, 3. This is anti-clockwise direction. So the configuration of the molecule is S. So this is S. It is not butanol. This is a bromo derivative. So there is Br here. It is not a butanol. So there will be Br here. It will be CH3 CHBr, CH2, CH3. It will be 2-bromobutane. It will be S2-bromobutane. Now, what is the advantages of this RS system? It is more widely applicable than the DL system. Then configuration of compounds with more than one asymmetric center can be specified. So, now coming to the next point, that is racemization. What do you mean by the term racemization? A process of converting an optically active compound into a racemic mixture is known as racemization. An optically active compound that will be naturally either plus form or minus form. So this optically active compound, which is either dextro or levo, when we convert that to DL form or plus minus form, we call it as racemization. The process of converting an optically active compound into the racemic mixture is known as racemization. Here you can see plus or minus is converted to plus minus. Together, it is a racemic mixture. Racemization occurs through intramolecular rearrangement caused by heat, light, or catalyst. How can we bring about racemization? Racemization can be brought about through heat, light, or catalyst. Now, optically active lactic acid kept in contact with base undergoes racemization to form racemic lactic acid. Optically active lactic acid means it can be D form or L form. When such a lactic acid is kept in contact with a base, an alkali, it undergoes racemization to form racemic lactic acid. So students, in this session, you would have learned about how to assign configuration for optically active compound, an optical isomer. Then how to assign plus minus notation as well as D or L notation, or capital D, capital L notation, and how to follow Kahn-Ingold-Prelog's rule and give the configuration R and S notation, and also the term racemization, definition of racemization, and what are the ways by which we can bring about racemization.